Okay, so in the last lecture, we have started with your single machine infinite bus system. So, wherein we have covered the structure of a single machine in infinite bus system. So, after covering the structure, we just move towards the swing equation. Okay, so therein I left out some important things that I have to inform about the swing equation. So that I'll be covering in this lecture, and we will be completing the derivation part of the swing equation in this particular lecture. So coming to the point, so I have started with the swing equation. So swing equation I have started, but I didn't tell you the necessity of this swing equation. Okay, so why you have to know about this swing equation and where it will be used in particular, I didn't give specification with respect to that. Okay, now I'll be telling you this. So I have already told you that that stability depends upon the three main parameters: frequency, rotor angle, and then the voltage stability. And over there exists your rotor angle. Okay, so that rotor angle is the thing that is related to this swing equation. Okay, so if the rotor angle, del, the rotor angle del is experiencing any kind of oscillation, then these oscillations are mathematically given through your swing equation. I hope you are able to get it. That is, if a rotor angle del is experiencing some disturbance, you know, right? What are the parameters that are causing your rotor angle disturbance? We have already seen, and particularly to that disturbance, this rotor angle, okay, that is your rotation in the rotor angle, that is with respect to your center of your shaft and your rotor. Okay, so that corresponds to your rotor angle, and if there is any oscillation in that rotor angle, it can be determined as a mathematical equation through this swing equation. So the mathematical representation of the disturbance is particularly concerned with this swing equation. I hope you are able to get it. And that is the main reason for which we are going towards your swing equation. So that is, a disturbance has been occurred, and you have to know about that magnitude of the disturbance, and the magnitude of the disturbance with respect to rotor angle is given through your swing equation. So that is why we are you have to have you're gaining knowledge about this swing equation. Okay, so I'll be giving a recall about what we have seen in the previous lecture, and we'll be finishing this derivation. Okay, so as you know, this corresponds to your unbalance in the system. So whenever an unbalance occurs, there will be a variation in the torques. Okay, so that's what given in this particular equation. So you know that TA is your accelerating or decelerating torque, Tm corresponds to your mechanical torque, and Te corresponds to your electromagnetic torque. Okay, this also we have already seen. If the if the Tm and Te are positive, then it is corresponds to your generator mode of action, and if your Tm and Te are negative, then it corresponds to the motoring action. Okay, so the combined inertia of the generator and the prime mover has to be taken into account. So that I have told through this diagram. You have also have to take into account your moment of inertia of the both of the what you can say, yeah, your shaft, that is your prime mover, and the rotor of the generator. The two moment of inertia you have to consider, and these two moment of inertia will be based entirely upon your angular velocity. and that's what over here they have given. These two will be depending upon your both angular velocity. So here J is represents the combined moment of inertia. J represents the combined moment of inertia of your generator and turbine, and omega m represents the angular velocity of rotor. And here you have to see it is in mechanical radian per second, and hence it is given in the omega m. Okay, so don't get confused. So if it is in omega r means here it will be electrical radian per second. So that's what the variation. The variation will be coming with respect to your unit. So m corresponds to your mechanical radian per second, and r corresponds to your electrical radian per second. And you know that t is nothing but the instance of time. Okay. So after this, we have moved towards to the representation in your per unit system. So we have already seen that importance of the per unit system in the previous units, and we are converting each and everything into the per unit system. So as per that, if you are converting your moment of inertia in case of the per unit system, so you have to divide it by your base power. You have to divide it by your base power. So here, this is the equation for converting your moment of inertia from your actual value to your base value. From your actual value to your base value. And after converting it to the in terms of per unit concept, we will be applying it into the particular equation. That is, this equation will be applying the value of j. So you'll be getting 2h by omega naught m square into apparent power, nothing but VA base, okay, into d omega m by dt Tm minus T. So this you will be rearranging, okay. You will be rearranging, and one of the yeah, after rearranging you will be getting 2h d by dt, and this d omega m by omega naught square m you will be having, and then Tm minus Te. And this is where you have to see, that is your angular velocity. So this corresponds to your angular velocity of the rotor in mechanical radian per second, and this corresponds to the angular velocity of the rotor at the initial point, okay, at the initial point that you have to see. But both are represented in mechanical radian per second. Still we didn't move towards your electrical radian per second, okay. So still we are in the mechanical portion only. And coming to the next part, here you are representing your base torque. So your base torque is given as the relation between your base power divided by omega naught m. That is your initial angular velocity, and this you already know. So that is your power value is equal to T into omega. So that's the formula over here they have used. So now you are representing in the per unit format, and here while representing in that, what happens, this omega r dash right here over this there, right, and this is nothing but the ratio between your omega m and omega naught m. So it is more or less similar to that of representing the base value of your voltage, okay. So in your voltage you will be representing, right, so like that, similar to that, here we are representing in a ratio, that is the actual value divided by your base value. So here the base value is nothing but the initial value, okay. And after this, here you can see, till this we are speaking everything with respect to your mechanical angular velocity, okay, mechanical radian per second. So after this point, we will be converting this into the electrical radian, that is electrical angular velocity. That is the angular velocity will be represented with respect to your radian per second. Okay, not to, we are converting from mechanical radian per second towards your electrical radian per second. So that's the key point over here. And while converting from the mechanical to electrical, you will be dividing it by the number of field poles at the stator. So this PF corresponds to the number of field poles at the stator. So this equation you might have studied at your machines too. Okay, the same thing is we are using, and these two are ratio. These two are ratio, and hence this will be cancelling and this will be cancelling. And finally, we have converted the angular velocity from mechanical radian per second towards electrical radian per second. So at the input of the generator, you will at the input of the generator, we will be corresponding towards your will be in the concern will be about the mechanical power. But while coming with respect to the output, the concern will be with respect to your electrical. So that's what over here happens. So after the conversion, we will be sticking towards your electrical quantity only. And for that only, here we are converting from mechanical radian per second towards your electrical radian per second. Okay, so here it is given. So your omega r corresponds to your angular velocity in electrical radian per second. Omega naught is the rated value, and PF corresponds to the number of field poles. And here, up to this we have seen in the last lecture, and after this, your del corresponds to the angular position of the rotor. Okay, so this is very important. This del is nothing but the angular position of the rotor in electrical radians with respect to the synchronous rotating frame. So here the synchronous rotating frame is nothing but the reference frame at the stationary point. So with respect to that, how much the angle of the rotor is moving is referred to be the del, and del naught is nothing but the initial value of this del at the time period t equal to 0. At the time period t equal to 0. Okay, I hope you are able to understand. So with respect to del and del naught also, we will be seeing the relation in the next slide. Yeah, this is a very important equation. So here they're defining your del value. Here they're defining your del value. So they are giving the relation between the del value with respect to the angular velocity. With respect to the angular velocity at the what you can say at the actual value and then your rated value. So here omega r represents your actual value and then your rated value. So with respect to this, we are defining your del. And here you can see the relationship between your del and then the time period t. Right? So here you can see the relationship between del and time period t. And this is what is a very important equation through which you can interrelate your frequency and your rotor angle. Through which you can interrelate your frequency and your rotor angle. You know that this time period t is the reciprocal of your frequency. So it will be 1 by f. And hence your del will be inversely proportional to your f through this equation. Through this equation, you can tell that your del value will be inversely proportional to your frequency. So if the frequency increases, your del value decreases. If the frequency decreases, your del value increases. So this is an important equation that relates the relationship between your del, your rotor angle, and your frequency. Okay, and after this, we'll be taking the time derivative. Okay, we'll be taking the time derivative. So actually, what we are doing over here is that why we are taking these things and all, you might be asking. The thing is, we have to in this thing over here, we don't know the value of d omega r dash by dt. This value we don't know in this first equation. And for that representation of this d omega r dash by dt, we have to find some mathematical relation. And hence we are moving from your mechanical to electrical part, and we're taking a relationship between your angular velocity and your rotor angle. So we have to replace this particular parameter, and for that only we are doing these calculations. So now we have to take the derivative with respect to the time period, and after this you will be getting the value as here it is angular velocity minus of your rated velocity. So angular velocity minus of the rated velocity. So it is a particularly it is a difference. It is a difference in value. So hence you can take it as a del. It is a difference in value, and hence you can take it as a del. That is a change in angular velocity that you can take. Okay, I hope you are able to understand it. So again, we'll be taking a second derivative. Okay, in order to find this this value d omega r dash by dt, in order to find this d omega r dash by dt, we will be again taking a second value for a second derivative for this d del by dt. So if you're taking the second derivative for this, so here d del omega r by dt will be coming out, and this del can replace with your d omega r by dt. And now what happens is that as per what we have seen in the relationship between your mechanical electrical radiance and electrical radiance. So here you can see your omega r dash can be represented by omega r by omega naught. So this omega r will be replaced with respect to your omega r by omega naught, and hence you will be getting the value like this, omega naught into d omega r dash by dt. Okay, so with this thing you can easily get the value of d omega r by dt. You can easily get. So you'll be having this at your left side, and other parameters you'll be taking towards your right hand side. Okay, so omega naught into d square del by dt square will be getting the value, and that you will be substituting in your equation 1. We'll be replacing with replacing by the d omega r dash by dt with this parameter. So now you will be getting this, and omega naught will be in the denominator. You can just take it towards your the other side to put omega naught tm minus omega naught te. Okay, and this is a you can also conclude with this equation. So you have mostly got the swing equation characteristics, but there is some variation. There is some variation that we have left out, and here you can see before getting to the next step. Here you can see this particular equation is in a second order, right? So it is in the second order. So what does a second order system represents? It's a basic mathematical question. What does this second order equation represents? So always the second order equation represents your oscillations. The second order equation represents your oscillations. So that's what you might have learned in your control system also, right? That's what you might have learned in your control system also. So this will be your amplitude, and this will be your time period. So this second order equation corresponds to the oscillations experienced by your rotor angle. So this is the thing what we are in need. This is the thing what we are in need. We are in need to represent the disturbance of the rotor angle in particularly in your as a mathematical format, and hence we are getting it in the second order form. Okay, so hence we are moving in the right path. So moving on, apart from this torque, you have to also consider another particular torque that we might have left out. That is, over here, as I said, you will be experiencing the oscillations, and you might have studied in a control system that for every oscillating system there will be a damping torque. There will be a damping torque to reduce these oscillations. To reduce these oscillations, there will be a damping torque. So you have to add that damping torque factor also. So this is the particular parameter for with respect to your damping torque. So to Tm minus Te minus Kd, so this is the damping torque constant, del omega r dash, that is your change in your angular velocity with respect to your in terms of your electrical radiant. Okay, so that's what here they are saying. This represents the swing in the rotor angle del during the disturbance. Okay, so this is the equation that representing your rotor angle disturbance. Okay, so here you can see there will be the interrelationship between your mechanical quantity as well as your electrical quantity in this particular equation. Okay, and we have represented this in the in your what you can say with respect to your torque, and next you have to represent this in your with respect to your power. With respect to power, you have to represent. And before getting into that, we will be coming with some conclusions through the particular equation. That is, during disturbances, the oscillation del, that is the oscillation at the rotor angle, is superimposed on the synchronous speed omega naught. Okay, so these are some of the key inference that we have to take, because here you can see your del is also related with your omega naught. That too, particularly your second order del. So that is, this corresponds to your oscillation. That oscillation is also depending upon your omega naught. So if you're bringing this to your right hand side, this will be directly proportional. Okay, the oscillation will be directly proportional to your angular velocity. Okay, that will be your rated angular velocity. So that's what given over here. And after that, the speed deviation is very much smaller than your omega naught. So this is what your speed deviation, and the speed deviation is very much smaller value that you already know, because it is nothing but omega r minus omega naught. Okay, and hence it will be very small. The generator speed is practically equal to your rated value. Yes, of course it is, because this is what your rated value. All your synchronous generators uh, will be rotating in your synchronous speed. So it is a must. Your synchronous generator has to rotate in the synchronous speed or the rated speed in order to have a smooth operation. So that's the another inference. Okay, so these are the inference that we can take from this swing equation, and the swing equation with respect to your power is given over here. So this is the final equation that we have to see. So it's nothing but the swing equation what we have seen before, but the thing is that we are converting everything into with respect to your power. We are converting everything with respect to your power. Okay. So this PM corresponds to a mechanical power input in per unit. Okay. So still we are considering everything in terms of per unit. And then P max will be corresponding to electrical power output in per unit. So H is the inertia constant, and del corresponds to a rotor angle. Okay, so this is the final equation, and you can consider this also to be a final equation. Okay, based upon the problem how they are asking it. Okay, so this is what with respect to the swing equation, and these are the inference that we can take with respect to the disturbance of the rotor angle. And so with this the swing equation gets over, and you have to move in a step-by-step fashion to determine this equation, swing equation. Okay, so that's a very important thing that we have to consider. Okay, so